nanohub.org.
Online simulation, and more for nanotechnology.
Professor Evan Reed from the Department of Material Science and Engineering at Stanford University. So when I was a graduate student back at Stanford University, I still remember I took two courses from Professor Evan Reed. So it's a great pleasure to see him presenting his recent research in this workshop. So if you are ready, you can start.
Great, fantastic. Well, it's good to see you again, Lily. I'd like to thank Elif and the other organizers for putting together this very interesting session and workshop on a very relevant topic. And so this particular talk is really aimed at the question of synthesis and how to predict which types of materials are likely to be synthesizable. So if we're going to invest a large amount of effort in trying to synthesize some range of materials, how do we sort of leverage our physical intuition and also available data, put these two things together to try to predict, what's the full spectrum of possible materials that have a particular property that we're interested in. So this focuses on two-dimensional materials, and this is really a primarily data-driven approach, and historically there have been a pretty broad spectrum of ways of trying to predict when something is synthesizable. This is really a sort of data-driven approach, and it's possible because of some recent data sets that we put together. So the take-home message here is that we've been able to identify what we think are over 1,000 layered or 2D materials that have yet to be synthesized, but are likely to be synthesizable. And to some extent, we've also been able to predict their properties, like their bandgap and some other properties. And so I'm going to walk you through how this works, how we did this, and what's good and what's bad about it. In particular, I'm going to talk about some new chemical families of layered materials that are predicted that have not yet been synthesized. Some applications, talk a little bit about phase change materials. So if you're looking for 2D materials that have specific properties, this can be useful. And also I'll talk a little bit about what was touched on in the last talk, this question of human comparisons. And how do we know, for example, whether our model is really doing as good as, say, a sort of inorganic chemist who really understands the rules of synthesis. And to do an approach like this, the key ingredient is data. And our experience has been, we've been doing this for maybe 8 or 10 years, and our experience has always been that data is the key. So getting some kind of signal out of the data is really 80% data and data curation. And so I'm going to talk about how we came up with data. So in order to do this, you need examples of lots of materials that are layered or have 2D nature. And you also need examples of materials that are either not synthesizable or are only synthesized into non-layered structures. And the latter part turns out to be the tricky piece. And so I'm going to talk about data, how we came up with these data sets, and how our thoughts are evolving on this, because that's really, I think, the key piece of this. So first of all, let me talk a little bit about our data. So how we came up with our examples of layered materials. We have developed an algorithm that will go through the atoms in a unit cell of a crystal and determine, just based on geometric considerations, which atoms are strongly bonded and which atoms are weakly bonded. And this allows you to break up the unit cell into these components of strongly bound units, like this 2D material, and then sort of weaker interactions between the layers. This is done using a just pairwise tabulated covalent bond distances plus some kind of threshold. So this is really pretty crude. It's really just based on atomic distances. So once you have the bonded units within a unit cell, we use a dimensionality or a sort of topological type algorithm that tells us what the dimensionality of the subcomponents of the unit cell are. So for example, if your unit cell is an organic molecular crystal, you've got this kind of blue dot molecule here that exists in your cell. And then if you make a 2x2 supercell in 2 dimensions here, and you rerun this algorithm, you will find that now you have 4 molecules or 4 bonded units. And that means that your unit cell consists of molecules or 0-dimensional types of bonding. However, if you have, let's say you have 1-dimensional wires, like atomic chains of wires that are running through your unit cell in one particular direction, then if you do this trick and you rerun the algorithm, you'll find that you only have 2 bonded units. And so that says, well, now you've got 1D wires. And likewise, if you do the same thing with 2D layers, then you wind up with 1 bonded unit in this 2-dimensional example. And it's going to be extended to 3 dimensions, which we've done. And it will parse your unit cell into these different dimensionalities as subcomponents. This algorithm works if your layers are not flat. Let's say your 2D layers are kind of corrugated, which sometimes happens, or have some other complex structure. This algorithm still works. So this is the idea. It's pretty simple. And we took this algorithm and applied it to tens of thousands of known crystal structures of materials that have been synthesized and characterized at some point over the last several decades. And we came up with over 1,000 2D materials. And so here's some of the mugshots of these guys. They have a pretty diverse spectrum of both properties and also structures. So for example, there are a lot of these that are oxides, and they have quite a bit of ionic bonding, unlike the TMDs and a lot of the other materials that are commonly studied. And furthermore, many of these have very complex structures, like this one's, say, 8 or 9 atoms thick. Each monolayer is 8 or 9 atoms thick. Some of these also have multiple polymorphs or multiple structures. This guy here, this manganese phosphorus compound, has a structure that has flat layers, and it also has a structure that has some kind of broken symmetry in these corrugated layers. And these are very similar in energy, and you might be interested in maybe using these as phase change materials if they have a large electronic contrast. Also, there are a large number of materials that have perforations. So unlike graphene and the TMDs and boron nitride and others, these have holes in them. And maybe for say ion filtration type applications, you might be interested in something like this. And so there's a pretty large spectrum of properties and morphologies of these materials. And I'll also just add, if you're interested in seeing these and actually looking through each one and to some extent knowing what its properties are, you can go to this paper. You can scan this QR code, which will take you there. And in the supplementary information, there's an Excel spreadsheet that has all these materials in it. And I will also recommend that if you want a larger list. So we keep running this screening. So we did this work maybe 5 years ago. And we keep running the screening as more structures get added to the crystal structure database. And the last time we did this was last fall in October, and we came up with almost 2,000 2D materials. And so the spectrum of the known 2D materials is really growing. So this is, at the time we published this paper, it was a little over 1,000. And if you want the latest database, go to our website. And I think there's a data link on there you can click on and download the latest version of this database that has almost 2,000 2D materials. So if you parse these into chemical families, you find that the one that has the most examples is are the TMDs, and maybe that's not too surprising. These are the molybdenum disulfide, tungsten selenide, these kinds of animals, and but there are a lot of others. And in fact, one of the surprises here is that more than half of the materials in this database do not belong to a chemical family, meaning there's only one particular example of a 2D material that has this particular chemical formula or stoichiometry. And what that means is that you would never find these just by exploiting structural analogies. So we can find a lot of TMDs just by, if we know MOS2 has a layered structure, it's a pretty reasonable bet that tungsten diselenide also could have a layered structure. And so you can kind of work through chemical families by exploiting these analogies. But over half of these materials, that doesn't work. And so that really points up the utility in having these huge crystal structure databases that many people have put a lot of work into over the decades to piece together very carefully. And so that was one of the surprises. We were worried that we were just going to find half of them are TMDs and the other ones we already know. But it turns out there's a lot of oddball types of chemical formulas that show up in this database. These are band gaps for the spectrum of 2D materials. And these are, DFT. Some of these are plus U gaps. So I would sort of take this with a grain of salt, but we're just trying to get a sense for what the spectrum properties is. And so if you believe these band gaps, then about 300 are metals. So there are lots of other metals beyond graphene, maybe for use as heat spreaders or other types of metallic applications. And then, depending on what you're interested in, there's probably a band gap for your particular application within this set of materials. In fact, there are even some really high band gap. There's quite a few oxides that show up in this layered database. And so if you're interested in insulating applications and you don't like boron nitride, there are actually quite a few other very large band gap materials that show up here. So that's the database. So now we have a kind of unique opportunity because we have over 1,000 examples of things that are layered. And presumably, if we're careful, we can put together a database of materials that are either synthesizable but not layered, or just not synthesizable at all. And so we have examples of these two categories. And the idea here is to try to construct some kind of empirical model. And this is really empiricism. I don't believe in machine learning magic. There's no magic here. This is really just empiricism. And let me walk you through, in this particular paper, let me walk you through what we've done. So we've done a lot of work since this in our understanding of this, of what's relevant for synthesis has improved. So let's say you have a chemical formula, MOS2, and you want to know whether this is likely to be synthesizable into a layered form. And so one way to do this is to first deconstruct this chemical formula into some set of features that describe properties that we think have some relevance for synthesis. And we don't have to know exactly for sure whether these are relevant or not. But these might be things like, for example, the average electronegativity of the elements that comprise the chemical formula, weighted by stoichiometry, or the average atomic weight of the elements, or let's say the standard deviation of the maybe the row or column in the periodic table of the elements. These are things that maybe plausibly could have some correlation in conjunction with other features to whether something is synthesizable or not. And so we put these all together. In this particular case, we want to stay away from structural features to the extent possible. So we want features that are really based only on the chemical formula, because we would like to screen millions of candidate materials for their potential to be layered, and we don't have the structure before we do the screening. And so we're really kind of limited to just chemical information about the formula and the elemental properties of atoms in that formula. So we construct these features, and in this particular paper, we've got about 100 of these things. And we talked to synthesis chemists, and we kind of came up with some list of features. And these provide input to some model. And for most of what we do, because we're working with materials data, the data sets are really quite small. Something like 1,000 data points is pretty luxurious for us. And so I try to steer everybody in my group away from very flexible models like neural nets. I like to stick to linear things, linear regression, logistic regression, and support vector machines with no kernels, in part because we have a much better sense for when we're likely to be overfitting and when not. Because just anecdotally, about 95% of the time, a student or a postdoc comes into my office with some results and some machine learning, it's almost always overfit. And I think that's largely just because the data sets we have are small, and overfitting isn't typically taught in a lot of CS classes, just because there's usually so much data in other applications that it's really not as much of an issue as it is for us when we have these really tiny data sets. So I tend to steer toward these kind of linear models, like linear regression or logistic regression. And in the case of a classifier, these models will predict whether something is layered or not layered. And so we start with the chemical formula. We have an algorithm that's very fast that predicts whether something is 2D or not synthesizable. And to train this model, we have our examples of things that are layered, and we also need to come up with examples of materials that are not layered or not synthesizable. And that turns out to be the tricky piece. So unfortunately, there's no database of stuff that is not synthesizable. Nobody's bothered to put that one together. And so we have to kind of use our intuition and figure out how should we piece these negative examples together. So what's the problem? Well, the problem is illustrated here. So this is just for carbon. So let's say we're interested in carbon. Carbon has one known layered phase, or actually at least one known layered phase, amongst a bunch of others. There are other ways that carbon can form. And so if you go to the crystal structure database and you look at carbon, you would say, well, this is a layered, we're going to classify this as a layered material because it has at least one known layered phase. But let's say that database is incomplete, and maybe there is a layered phase of carbon, but it hasn't been synthesized or hasn't been reported, or maybe it just hasn't been scraped up and put into the database. So in that case, we could say, well, this is not layered because we don't see a layered phase, but it could just be incomplete data. And so you can see the challenge with this, or at least one of the challenges. And so we've got to make some assumptions about what's not layered in this particular case. And so our approach to this is really to try a few different definitions of being unsynthesizable or not layered. And the first thing we did was just to consider, just as I said here, just consider that anything in the crystal structure database that doesn't have a layered phase is really not layered. So there's no way to synthesize this layered form of this particular compound. So if you assume that, then schematically what you have is something like this figure here. So let's say the blue dots are materials that we're considering unlabeled, which means we're not quite sure. There's no layered phase in the database. We're not quite sure what that means, but we're gonna, for now, we're just consider them to be unsynthesizable as layered materials. And the red dots are layered materials. And there's some kind of mixing of these blue and red dots. And we started out with a support vector machine, which is just a linear model, which attempts to draw, in this two-dimensional case, it just attempts to draw a line that best separates these two colors of dots. And so it's a classifier. It's a two-state classifier. And let me just tell you, first of all, how this particular set of assumptions works. And there's really only two numbers that I want to focus on here in these results. So this is our test set. Our data set is big enough to really have an honest to goodness test set of about 368 layered materials and 10,000 materials that we're considering not to be layered. And the precision here is something we focus on mostly because when we work with experimental synthesis collaborators and we say, hey, can you go make this thing? Usually what happens is we give them a list and maybe they'll go into the lab and they'll make one of them. And if that one doesn't work out as expected, then they stop. And so there's a real strong, this is just a sociological driver to make sure that our precision, which is telling us essentially what fraction of the materials predicted to be layered actually are layered. There's a strong incentive to make that number as high as possible so that we can really give a list of candidates to our synthesis colleagues that are really likely to work out. And so in this particular case, the precision is about 40%, which means 40% of the materials predicted to be layered actually are layered. And you might say, well, that's not so great. Maybe 80 or 90% would be better. And that's true. But the thing to compare with is really some kind of baseline. So let's suppose that we're randomly guessing. And let's say you give me some candidate chemical formula, and every time you give me one, I just say, yes, it's layered, it's layered, it's layered, each time you give me one. In that particular case, our performance would be 4% because it turns out that about 4% of known crystal structures are layered. So if we're just randomly guessing, we're going to get 4%. And if we take the ratio of these two, we get about a factor of 10 improvement over random guessing, which in our experience for these kind of materials data sets is actually pretty good. Usually we're getting, if you're not very careful, you get a factor of 2 or 3, which is really very little signal. 10 is actually pretty good. And so this says we're doing 10 times better than random guessing, which is, there's some signal there. But let's now consider how important our choice of negative examples is in a different way. So let's suppose now that we don't like, that just assuming that everything in the ICSD that lacks a layered phase is not synthesizable as a layered material. And let's try to be a little bit more nuanced about this. And so we've approached this also using semi-supervised learning, which is useful in cases where you have a data set where some of the data have labels where we're confident there's a layered phase, and the other set is unlabeled. So there's some uncertainty about whether it's layered or not. And the idea is really simple. So I'm just going to walk you through how this works. So it starts out just like we did before, with just a standard, you train a model. In this case, we're using support vector machine. It puts some kind of dividing hyperplane between the two different data classes. But then we take that hyperplane and we measure the distance between the hyperplane and each of these unlabeled data points. And the ones over here that are predicted to be not layered by the simple SVM are given a weight. And the weight is simply the distance from the hyperplane of each data point. And the further that point is from the hyperplane, we assume it's more likely to be not layered. So ones close to the hyperplane are given a weight that's kind of around 0.4-ish, 0.5, 0.6, something like that. And then the blue dots that are on this side of the hyperplane are given a very high weight. And so this is kind of giving us, it's one way of giving us a probabilistic estimate for what the actual labels on our unlabeled data are. And you can pick through this. You can see, there's no magic here. There's a question of, is this a reasonable thing to do to label the unlabeled data? And that's a long art, sort of discussion that we can have. But the way that I look at this is it's just another way of labeling the unlabeled data points. And we want to study how robust our predictions and performance are with respect to this different set of labels. We hope that, when we change our definition of unlabeled material just a little bit, we don't get a massive change in the model performance and what it predicts to be layered. So once we have these weights, you just train another SVM, and you use the weights to kind of describe, what's labeled or not. And we get another line here that now separates. You can see it kind of does a better job of separating these two clusters. And what this would predict is that all these blue data points over here are actually probably layered. We just don't have a layered phase in the data set. And all these guys over here are not layered. So this is an alternative scheme. And to talk about the performance of this, let me show you in terms of a plot here. So this is the precision, which is what we mostly care about. And we also care about the compute time, because if we want to screen millions of materials, the compute time really matters. So if we're randomly guessing here, we're at about 4%, because that's our random baseline. So we want models that are better than 4% on precision. And this is how the semi-supervised model does. So we're better than 40% now. We're closer to 45 or 50% on precision. So it is a little bit better. I wouldn't ascribe a lot of physical meaning to that. I think it just means that there's some robustness to how we assign the unlabeled data. And but you might also ask, how does this compare with experts? Because of course, there's a lot of experts that have really deep understanding of when something is synthesizable and when it isn't. And so we put together a quiz that we gave to a spectrum of people doing research in this space. Most of the people we gave the quiz to are not synthesis chemists. They're mostly double E's and material science folks and mechanical engineers who are doing work on 2D materials and would like to be able to predict new materials, but they're not trained in synthesis chemistry. And so the quizzes look like this. So there's 55 materials here, chemical formulas. These are all known to exist. They're all in the crystal structure database. They have been synthesized, and only one of them is actually layered. And if you're like me, you're like a deer in headlights with this quiz. I took a number of versions of this, and I got zeros on all of them. And it turns out in this particular case, I think it's number 16 that's actually layered. And so if you guessed that, good for you. I never would have guessed that. So anyway, so we gave this quiz to a spectrum of individuals, and the practitioners, so these are the double E's, the mech E's, the material science folks who are using 2D materials, they did better than random. So that's good. They have some intuition, but not a whole lot better than random. And furthermore, it took them a lot of time, because they were Googling things and they were using the structural viewer to kind of, or they were sort of online doing things. And so what we want are algorithms that are really fast over here and have high precision. So we want stuff that's kind of up here. And we also gave this quiz to a small number of real expert synthesis chemists. And one of those individuals was Josh Goldberger at Ohio State. And he actually, he took a number of these quizzes. So we took a kind of average over about 10 different quizzes. And he did comparable to the algorithm. And he was the best, he had the highest score of everybody. And he really thinks about these things. I think he teaches a class on kind of this area. And so he's really thought deeply about, what matters. And he came up with a set of rules for how he did it. And more or less, his rules are included in our feature set. And so it's not too surprising that they kind of wound up performing similarly. So that makes us happy about the sort of completeness of our feature set anyway. And so the value here is that, we're not trying to replace humans. I'm skeptical about, at least with the typical sizes of materials data that we have, I'm really skeptical that these models are going to do much, if any, better than experts. And in most cases we've seen, these are basically comparable to what experts can do, but they can do it a lot faster. And so if I send a million materials to Josh in an email, he's not going to write me back. And it's going to take him a long time to screen through these. So we want these algorithms that can do it quickly in an automated fashion. And furthermore, that these folks can use, the people who are not synthesis chemists, to find the materials that they want. So that's the value added here, I think. So this model does about 5 times better than most of the practitioners working on 2D materials. And it does about 10 to sort of 13 times better than a random guessing baseline at identifying these materials. So we have this model, and now you can screen. So you can just run a bunch of chemical formulas through. There's some actually quite a bit of subtlety here also in how you identify these chemical formulas to screen, which I won't talk about because there's no time. But what we came up with is about 1,000 chemical formulas that are likely to be synthesizable that have yet to be synthesized. And that adds to about 1,200 or 2,000 known layered materials. And so that says that there really are limits to the spectrum of layered materials when you define them in this way. And we're about halfway there. So we've synthesized about roughly half of the possibilities for layered materials. And furthermore, you can predict, to some extent, you can predict properties like the bandgap here. We've tried to predict these are candidates for each of these bins of bandgap. This is quite a bit less accurate, but because the data sets are smaller, once you parse the data into these kind of bandgap subregions, your data size shrinks, and so your accuracy goes down. But to some extent, you can do this. And we've also tested some of these predictions using DFT. So this is really a kind of a crude test of the model, but essentially what we found is that we took 16 predicted cases. We did DFT calculations to test for layered stability in layered forms. And we found that 13 were right. So 13 of these predictions were actually stable as layered materials. So this is kind of consistent with the precision being something like 50%, something like that. And we found some of these have multiple phases. So this zirconium compound, for instance, has several different layered phases, which could be useful for some applications, maybe phase change types of applications for layered materials. So lastly, this is my last slide. You might also say, well, maybe this algorithm is just doing what I talked about for the TMDs, or it just takes known chemical formulas and just does, atomic substitutions into those. And that's really all it's coming up with. And so maybe you could just really guess all the predictions of this model just by doing atomic substitutions on these 1,000 known structures. So to test this, we categorized all the predicted chemical families, which are shown in the blue bars, and compared them with the known or synthesized layered materials, which are the red bars. And we do find that in many cases, the algorithm is just kind of doing atomic substitutions on known layered phases, like this one here. But there are cases where there is no overlap at all. And so in some cases, the algorithm is really predicting new chemical families that don't exist in the layered database. And so it's doing a little bit more than just atomic substitutions. And of course, the acid test for all this would be some kind of synthesis of a large number of these materials. And that's something that we, those of you who do synthesis is hard. We just heard in our last talk about automation, which is very exciting to me. But that's the acid test. That's what we'd like to do, is just have, say 20 of these synthesized to see what the statistics are and how many new layered materials we can find. So lastly, and most importantly, I want to acknowledge the people who actually did this work. Go-Eun Chun was the leader on this project. She's a 6th-year PhD now. And there are a couple of papers on this work. And we also worked with Dosh Chubuk, who was a postdoc with us. He's now at Google. Evan Antoniuk is a senior PhD also. And I especially want to thank Josh, who helped a lot with this, with building intuition and also being brave enough to take this quiz, which was really, I think, quite brave on his part. So with that, I will conclude and turn it back to Lily for questions, if you have any.
Thank you, Professor Reed. So now let's turn to the attendees to see their questions. So there's one question in the chat section. You can talk with your question to Professor Reed.
Yep, thanks for the excellent talk. So we are experimentalists, so we would like to work with you more in terms of with the modeling people. So I was just wondering if we can, so for example, if we'd like to make a new material, layered or non-layered, but based on the talk, we can only do the predict and the actual calculate the bandgap and other properties before when we have actual materials. Can we do in a reverse way? So for example, if I want a material with a bandgap of silicon, with a mechanical property of diamond, and I don't know, a thermal heat conduction of the diamond as well. So can we do based on the bandgap, based on optical properties, and find appropriate material, analyzing the whole periodic table? I think it's a little bit too futuristic, but I was just wondering if is there any possibilities doing that?
It is, and that's actually what we've done here. So these are not, we haven't done DFT calculations on these materials. We don't know the structure. This is just where what we've done in this particular case is we've taken our training set and we've parsed it into these different bandgap regions. And these are DFT band gaps, so you can.
Yep.
You can, but anyway, so we parse it into these different regions, and then try to predict materials that are both layered and have this particular band gap range. And so you can do that trick. The challenge is that as you get more fine grained, let's say in band gap, let's say you really want something near 1 EV. And, within a tenth of an EV or something, the size of your training data suddenly gets very small because there just aren't, there are much fewer examples of materials that have that particular property. And so the accuracy of the predictions goes down quite a bit.
Oh, okay.
And so there's really a trade-off between how accurately you want to be able to predict some property and the data that you have. So that's the price you pay. So the accuracy of these, I think we were getting something like 50%. So there's like a 50% chance that each of these materials actually has this band gap in this range. And so, if you're making these things, maybe you'd have to synthesize several to get one that really has the property that you want. And so as long as you're willing to do that, it's fine. But if you're going to stop after one synthesis, then these are not really good enough for your purpose.
Thank you.
And by the way, we love to work with you because we, I think really, trying to grow a bunch of these would be very useful. I think it also, there's a lot of machine learning in our community, and we'd really like to see this validated by experimental efforts. I think that's really the key, the way to go forward with this.
Thanks, Professor Reed.
Along those lines, if you don't mind, I have a question, which is, of these unpredicted families, has any experimentalist actually been able to synthesize any of them, to your knowledge?
Yeah, so that's something we're starting to be in a position to check. So basically, we did this work like 4 years ago, and we can go back to the literature now and the databases, and we can see what's actually been synthesized. And so we're actually starting to do that. But I don't have an answer for you. But that's a very great question, because that's the acid test.
Exactly. That would be very exciting now that it has been a couple of years to actually get that feedback.
Yeah,
and that would be amazing.
We're working on that.
I have a follow-up question. So there are some materials you predict to be layered, but they do not exist. So for those materials, are they a metal stable phase that need special or unique temperature or pressure to make them, or they need some special conditions to control the kinetics of the growth to realize those materials?
Yeah, that's a great question. So why, what's the story with the 60% that we predict to be layered that are not? And the answer, I think, is really it's a mix of a lot of things, because our model is only as accurate as the data. The data are collected from the literature. And so these are materials that, someone has been able to grow in the lab using a large spectrum of techniques. And so the ICSD, there's a huge spectrum of growth techniques that are used to produce those materials. And so there's nothing specific about the method here. We've in more recent work, we've been focusing on kind of breaking this down into different synthesis types. But for this work, it's all just lumped together. So there's nothing specific about synthesis. And furthermore, there are sociological kind of human factors that are interwoven, implicit in this data. Like, there's not a lot of, say, radioactive materials in the database. There are some, but it's because they're dangerous to work with, and maybe you can't work with them in academic settings where a lot of this work is done. And so there's a lot of these kind of human factors that are implicit in the data, and it may well be that something that is predicted to be unsynthesizable actually is, but maybe you just need to use radioactive elements, and the model thinks that those things are not going to form layered compounds because there's no data in the database. And so it's difficult for me to provide a really fine-grained answer to that question, just because there's so much baked into the data. It's not just all chemistry. It's really other things. Cost of elements maybe matters too. You might have more experiments with cheaper elements. Those are the kinds of things that we've been thinking about more recently, and trying to understand how much of what we've made is really driven by physics and chemistry and what's possible versus these other kind of sociological driving factors.
Okay, thank you.